So this is where we're at. We have seen the set of solutions of the homogeneous equation defined by B is given by those points. And since B and A are only related by an invertible matrix, which doesn't change the solution of the homogeneous equations, this is the same as LA0, which is good, because as we've seen, we get all solutions by getting the homogeneous solution and one particular solution of the equation. So to get some particular equations, so we have, we had B prime. This was we had studied the system AX is equal to B. Just to recall, we had started with AX equal to B, which is equivalent to BX equal to B prime, and this B prime is then contained in the space KRM, which we didn't call like this at the time, but this was just, since we had a solution by assumption, this means that kind of all the entries in the last entries are vanishing, so this means B prime must be in that space. Now, since we're in that space, we can find a particular solution simply, by definition of this map Bj, by construction, we have a unique pre-image, Bj to the minus 1 of B prime. So this by construction is contained in the, or by definition of this map, this is contained in the solution set LB B prime, but by construction this is the same as LAB. So this means this is how we get a particular solution somehow. This is a uniquely defined map. This is an isomorphism, so there we have some point. So this means we have a homogeneous solution and we have one particular solution. So this means our solution set looks as follows. The set LAB is given then by, so all solutions of this form, minus Bj minus 1 By plus the particular solution, which is Bj to the minus 1 of B prime. So by all points of this form k to the n, where y is in Vj. And this can maybe also be written in a more concise way, just to have this once on the board. This is Bj to the minus 1 of B prime minus By, just by linearity. So just to have it there. So when we look at the claim follows now. Since we have now constructed our point, we have to find this point C and we have to find this map G. And this is now obvious from this description here. The claim follows with putting this to be C. And G, this map small g that we had in the assertion, this must just be this point C, let's call it already C here, and this here. So minus Bj minus 1 By, which is uniquely defined. So this does the job. Now, this looks, we now have this theoretical result, how to describe this. But the good thing is, as I said, the proof is very constructive. So we now have a machinery of how to do the proofs and of how to compute the solutions. And before I do the example, let me line out the general method that we can now derive from this. So the method for finding solution sets of linear systems. Okay, and this is now just simply in a number of steps how we can do this. So, first of all, we interpret such a, this is what we started with, so let me just keep this down. We interpret this general system, which I call star, so this very general system of linear equations, as an equation of matrices. So this was what we started with. We viewed this as AX is equal to B. So explicitly, so we have this coefficient matrix A11, A12, A1n, and so on to AM1, AM2, and so on to AMN. Okay, this is equal to this B1 to Bm, where all the quantities here are defined as in this system star. So, oh sorry, the crucial part is missing, times x1 to xn. Of course, we need variables here. So this is now the equation, it's an equation of matrices, so this was what we started with. Then what we did, and this is so the method that we used always, we went back to the row echelon form and first checked if there is a solution. So we have to apply again, so by bringing this into row echelon form, it was always done by elementary row operations, and this is also the way we have to do this. So let me abbreviate them again as ERO. Elementary row operations and now the idea is that this is how we transformed this matrix A into a matrix B in, so if this is, okay, this is A, just here. So we had always transformed A by the same matrix as we transformed B to preserve the systems of equations. So we apply elementary row operations to both A and B, so both on the left and the right-hand side. To obtain B in row echelon form and some B prime in Km with Ax equal to B is equivalent to B prime X, Bx is equal to B prime. Okay, and now if we have this row echelon form, we can now first make the check if we have a solution. So use theorem, that was 867, to check if Bx equal to B prime has a solution. So if not, then Ax equal to B cannot have a solution. So here, if not, then we cannot have a solution. So then LAB, the solution set, would just be empty. Okay, so much for that. But if we have a solution, so if not, then this. If it has, then we have to kind of do this procedure of this theorem. So first of all, find Uj and Vj. This now looks maybe a bit, a bit awful, so to say. So this is something which is, looks hard, but as it turns out in the example, this is not that difficult. We just have to check the pivots and so on. Let me do the example, then you'll be happy. So find Uj and Vj as in theorem 868. Okay, and then once we have this, so what we did before was we took some element of Vj and found an element of Uj such that the sum is a solution of the homogeneous equation, and afterwards we added this one particular solution to get solutions of the inhomogeneous equation. This can be done in one step in practice. So this is basically, let me just write this down how it goes, and this is basically combining these two steps that I did in the proof there for each. So once this, I did this separately in the proof, so to ensure that everything exists, everything is well defined and so on. But once we know this, we can then abbreviate the method. So for each y in this space Vj, find the unique solution of the following equation of, the solution xy in Uj. And now we are modifying this a bit, so to get the inhomogeneous part of b xy is equal to minus by. This is what we did before for the homogeneous part, and now to get the general part, we add just plus b prime. If you take a look at the proof and think about this equation, this is basically just combining these steps. So just by our theoretical reasoning, this has a unique solution. This is what we know, and this is what we have to determine. So this is again a system of linear equations, which then can be solved explicitly, as it turns out, because this is a unique solution of this by Gaussian elimination. Gaussian elimination, and so on. So we will see the example later. So just this procedure, bringing this into row echelon form, and then reversing, so starting with the last equation, getting a solution for that variable, then the next, and the next, and the next, and so on, this iterative procedure to unwind the whole system. Then once we have this solution, these solutions here. Then we know that the solution set of, so LAB is just y plus xy. So the set of all these types where y is now in Vj. So this is how we get the whole solution set. Okay, now this looks awfully complicated, I have to admit, but let's take a look at an example and you will see it is not that bad. Because basically the only confusing thing here are the uj and the vj, I would say. So let's do an example. So I'm now doing a real linear system, so let's keep the complex numbers maybe for later. We consider the following system. The first equation is x1 plus 6x3 plus x4 is equal to 3. Second equation, x2 minus 8x3 is equal to minus 5. And finally, 4x2 minus 16x3 minus 3x4 is equal to minus 7. Okay, so how do we solve this? First of all, I want to write this as a matrix so we can have this scheme that we had before. So this is as a matrix equivalent to the following. So we have 4 matrices and we have here 3 equations. So this has to be a 3 by 4 matrix. So 3 columns, 4 rows. So the coefficients, this is now the coefficient matrix, so we have to check for the coefficients of the different variables here. So we have the variables x1, x2, x3, x4. Here we have 1 times x1, which is in the first row then, 0 times x2, it's always important to keep them as well, then 6 times x3, and 1 times x4. Okay, the same in the second row, we have 0 times x1, plus 1 times x2, minus 8 times x3, and 0 times x4. And here finally 0 times x1, 4 x2, minus 16 x3, and minus 3 x4. So this times x1, x2, x3, x4 must be equal to 3 minus 5 minus 7. This is what we need to solve. And now the first thing we need to do, so in this method, so we did the first step, so we interpret this as an equation of matrices, and now the second step, we have to apply elementary row operations to both sides to bring this into row echelon form. And it's quite easy to see what we have to do, but I'm running out of space, so let me quickly erase one last time. So we need to bring this into row echelon form. Now here we see, okay, the first column is already good. This looks fine. But here we have 2 different non-vanishing entries, so we just need to get rid of one of them. And so we simply do so by adding minus 4 times this to this. Then we get a 0 there. So we need to apply this operation E minus 4, 3, 2. So this was the abbreviation for adding minus 4 times the second row to the third row. And we do the same here. 3, 2. So we obtain, so 1, 0, 6, 1 as it is, then 0, 1, minus 8 is 0, and only the third row changes. So we get 0, 0, and here we now get minus 4 times minus 8 gives plus 32, minus 16 gives plus 16. And finally, here we add 0 to something, which is just leaves what it was, so minus 3. So we get this one times x1, x2, x3, x4. This must be equal to, and now here we have to do the same thing, so 3 and minus 5, and now we take minus 4 times this row, which is minus 4 times minus 5 gives plus 20, minus 7 gives 13. Okay, this is in row echelon form. So let's call this matrix B. So B is in row echelon form. And now we need to construct these spaces uj and vj. Oops. Okay. So what is j? J was the set of column indices of the pivots elements. So the pivots, which are now here, so this one, and this one. These are the pivot elements, the first non-vanishing terms in each row, which are just in the first column, the second and the third. So j is 1, 2, 3. Okay, now what do the spaces uj and vj look like? So then uj, so this is the span of the canonical base vectors with these indices 1, 2, and 3. So uj is x1, x2, x3, and the fourth component must be 0. So this is just this quite simple space. So this in k to the so in R4. So where x0, x1, x2, x3 is in R3. So, and then it's also clear what Vj must be. Vj, this is then just, yeah, all the other indices that we have, and there are not that many. It's just the last one. So we get 0, 0, 0, and let's call this y for a change. So to keep this a bit separate, in R4, where y is in R. Okay, now what we need in this method that you have erased, and so I cannot refer to this directly at this point, we just need to solve the equation. So given some element of this, so just some y in R, which we consider as a fixed number, we need to solve the following. We need that, so b of an element of uj, so which is in general of the form x1, x2, x3, 0. I'm a bit sloppy with identifying column vectors with elements of R4 again. So b times this must be minus b times the element of vj that we are studying, so 0, 0, 0, y, plus b prime, which is now this right-hand vector here. So 3, 5, minus 13. And this is now something we can compute. B is just matrix containing numbers. So if we now write this again as a system of equations, we get that, so b times x1, x2, x3, 0 in general is just, so again, the first row that we would get, so the first equation, if you consider the corresponding system, is taking the first row here, multiplying it with this, but this time when the element is of this form. So this means we get 1 times x1 minus, plus 0 times x3, x2, sorry, plus 6 times x3, yeah, and plus 1 times 0, so nothing. This would be the left-hand side in the first row. In the second row, we would get here the second row of that multiplied with this, which would be x2 minus 8, or maybe that's, sorry, let me write this a bit cleaner. x1 plus 6x3, so just to see this. Then we get x2 minus 8x3, and in the third row, we get this multiplied with this, and so this is 0 times x1 plus 0 times x2 plus 16 times x3 plus nothing because here's a 0. So, and on the right-hand side of the system, let's compute this as well. So here we need to apply minus and then b multiplied with this. So here, of course, so the first row we have to 1 times 0, 0 times 0, 6 times 0, and the last one is just y. And here we have the minus sign, so it's minus y plus 3 coming from there. So the same thing with the second row. Here we just see 0, 0, 0, 0, no y whatsoever. So we just get minus 5. And finally 16x3, and on the right-hand side we get this multiplied with this and the minus there. Wait, why do I have minus 5? It's, sorry, I forgot the minus here. Right, minus 5. Sorry, and now b times this, so in the third row, so we take 0 plus, times 0 plus 0 times 0 plus 16 times 0, and finally minus 3 times y, and since there's a minus in front, this is plus, so 3y minus 13. Okay, so please consider y is some fixed number. We consider this as fixed. So we get, this is now, since this is in row echelon form, it's now clear what we can do, because this is now easy to handle. So from the last row, we simply can just divide this by 16 and get x3. So from last row, from last equation, to be precise here. So x3 is 3 over 16 times y minus 13 over 16. Okay, not that beautiful, but this is where we're at. Okay, if we insert this now into this one, so insert into second equation, then we get our formula for x2, namely we get, first of all, x2 is, if we just bring 8x3 to the right-hand side, this is 8x3 minus 5. So this would be 8 times this. This means 3 over 2y minus 13 over 2 minus 5. Yes? Now I'm slightly confused. Sorry. I made a mistake with the signs. Here it's a plus. Sorry, I was a bit confused because I had remembered different numbers. There was a plus. Sorry about that. Yeah, here minus plus, so I just had the minus in the wrong part. So yeah. So here we get a plus, and now this is fine. Here we get a plus. Okay, this is better. So 3 over 2 times y. So we get x2 is 3 over 2y. And now we have 13 over 2 minus 10 over 2 gives 3 over 2. Okay, and this can now be inserted into the first equation. Insert into first equation, or not this, but the other term. And it turns out I can mess up a simple computation, so sorry for the cut. So we have to insert this into the first equation. This means at this point we need to use that x1 is, just bring this to the other side, minus 6x3 minus y plus 3. So let's do the computations here. So minus 6x3, so this is minus 18 over 16y, minus 78 over 16, yeah, like this, minus y plus 3, so let's simplify this. So this here is 9 over 8, this is minus 1, so this is minus 17 over 8. X1 is minus 17 over 8. Now comes the funny part. So 3 is, so this 3 times 16 is 48. So it's plus 48 minus 78 over 16. So this is minus 17 over 8 times y plus 30 over 16, which is minus 17 over 8 y plus 15 over 8. Ooh, okay, I hope this was the correct solution. Yes. No, it wasn't. It's minus. Yes, now it's correct. Okay, so we have computed x1 depending on y, x2, x3 depending on y, and so the fourth coordinate, this x4, this was the y we started with. So from this we get that the whole solution set, LAB in this setting, is given as follows. In the first coordinate we have this, so minus 17 over 8y minus 15 over 8. Then we have in the second component, where is it? 3 over 2y plus 3 over 2. Okay, x3 was there, 3 over 16y plus 13 over 16. And the fourth coordinate is just y. So this is the set of all solutions in R4, where y is just a real number, so for any real number. So to see that this is really in a kind of decomposition in terms of the homogeneous solution and a particular solution, we just basically sum out everything which doesn't have a y in it. So there's a fixed point plus something depending on y. Namely, this is the same as the set of all. So here we have minus 15 over 8. Here we have 3 over 2. Here we have 13 over 16, and the rest is just 0. So this is an element of uj. This is kind of in line with what we've shown so far. And this is the same plus y times minus 17 over 8, 3 over 2, 3 over 16, and 1 for all y in R. So here we can now see this is the solution of the linear system, which was element of this uj, which is kind of what we did in the proof to construct this uniquely. So we have this point plus, and this is now, this is basically the span of this particular vector here. So it turns out that the span of this is then the set of solutions of the homogeneous equation. So correspondingly when everything is 0 on the right-hand side. So this is how I get this really as a decomposition in these terms. Now, this depended only on this number y. In general, we could also have more numbers. So, for example, if we had something, if we have 5 variables, we could have something where we had x1, x2, x3 in this one side, and on the other side we had y1 and y2, and then we would have to determine x1, x2, x3 depending on y1 and y2. This always depends on the rank of the matrix. So in this setting, you could compute or you can check that the rank of the matrix is 2. So if the matrix had rank 1 that we started with, then we would have had the solution, the situation that we would have y1 and y2, so everything would be 2-dimensional here. But yeah, I will not go to this here, but this is kind of how to generally get all solutions of such a system of linear equations. Okay, so much for computations so far. This is the end of chapter 8 on matrices. So in the next chapter, we will also study matrices, but also linear maps. We will combine them in a particular case. Then we will focus on maps that go from a vector space over a field to itself. So maps from V to V, which are linear. This particularly means that the matrices that are involved, so the matrix representations and so on, are always quadratic matrices. And there are some constructions and some things involving these quadratic things that don't make sense for non-quadratic stuff. And also this being in one vector space to another, this is something which also frequently occurs in practical applications, also in physics. For example, if you have a rotation, this we will see later, for example, if you rotate something along an axis in R3, rotation is like a linear map from R3 into R3, or like any transformation of a given physical system, which is kind of given as R to the n coordinates. So if you apply some transformation of the system or apply something there, and this is always a map within the system, so to say. And this is what, this is the most important case probably of linear algebra there. And we will focus on that case in the next chapter. See you then.